So, zuerst mal herzlichen Dank für die netten Worte, Kollege Gerzerbeck. Ja. Auch ich erinnere mich an diese Biothermodynamik-Seminare. Ja. Das ist sicher etwas, was eine Universität ausmacht, dass man kreativ denken kann und so weiter. Und das ist dann keine Arbeit, sondern das ist eigentlich Spaß. Ja. Alle anderen Gäste, Freunde, Studenten, Studentinnen, ehemalige Dissertanten, Dissertantinnen, einmal Dissertant, immer Dissertant. Ja, das ist so. Ja, damit müsst ihr leben. Ich bin auch noch immer der Alois bei meiner Mama. Ja, also das ist, ja, das ist so. Ja, auch die Gäste von auswärts, ja, herzlich willkommen und danke, dass Sie gekommen oder ihr gekommen seid. Jetzt funktioniert es. Ja. Ich habe sehr viele oder mittlerweile viele englischsprachige Dissertanten, deswegen werde ich diesen Vortrag in Englisch halten, das war auch so angekündigt. Wir können nachher die Diskussion gemischt, Englisch, Deutsch, Brocklisch und so weiter halten. Ich sage meinen Leuten immer wieder, wenn sie schreiben oder diskutieren, die internationale Sprache ist bad English. Ja, so kommunizieren wir in der Wissenschaft. Ja, das ist das ist toll, vielleicht der Kollege Gerzerbeck hat schon angesprochen, Internationalität, da hat vielleicht die BOKU noch ein bisschen was nachzuholen, ja, das wäre schon, ich habe das jetzt gesehen, habe einige Dissertantinnen aus dem Ausland, also aus dem nicht deutsch sprechenden Ausland und das ist eine absolute Bereicherung, ja, auch für die Arbeitsgruppe. Also gehen wir in das Downstream. Let's go to the downstream processing of biopharmaceuticals. Have we reached the physical limits? Yeah? The problem is if we have reached the physical limits, yeah, then there is no need for a further professorship. So you know actually that we have not reached the physical limits. So the answer before. So today's menu is actually, I will talk a little bit about the discipline. Reingard, you told us that you had problems to understand the discipline, but now you know it, yeah? Maybe others have it, yeah? The product classes and production processes and biosimilars in biopharmaceuticals. Then the research question, do we have really a challenge and is there a grand challenge? Because we are actually asked in research programs like Horizon 2020 to answer grand challenges. Yeah? And then some state of the art and advantage, then some examples about the physical limits, and these are selected examples like chromatography, continuous processes, and some examples from their own laboratory. So let's go to the biologics market. The global biologics market generates a revenue of about 240 billions in 2016. I took this from the internet. Yeah? So everybody has rolling dollars in their eyes. Yeah? So, but the biologics substantially enlarged therapeutic options. Yeah? That's really important. We have definitely a highly expanded life expectancy through biologics. These are options for sports stopping, anti-aging, and what is really important, it stresses our healthcare budget because they are so expensive. Yeah? So there is in between the positive moment and is also the problem about how we actually buy and finance this new material. I don't want to go through all these details of the biological products, yeah, but we have the peptides and proteins, oligonucleotides, protein conjugates, virus-like particles, exosomes, and other extracellular particles. Microorganisms are relatively old, polysaccharides and vaccines, and recently also cells and tissues. Yeah? So here you see these product classes and what actually the problem is in manufacturing of this material. So here you see this is aspirin, yeah? A very small molecule, not a biological product. Here we have insulin, yeah? Very small compared actually to our other products like viruses or virus-like particles. Here, for instance, this is the size of Gardasil. Gardasil is actually a vaccine to actually protect against papillomavirus infection. Extremely successful with several billion revenue per year. And here is actually 60% of the entire biologics market. These are antibodies. And then you see, I could not draw it to scale, is actually the cells. Just to see the top 10 pharmaceuticals, and this is in the general public often completely overlooked, is that 7 or 6 out of 10 6 out of 10 are antibodies, and 8 out of 10 are biologics. Yeah? So in the pharmaceuticals market, yeah? So that biologicals are actually today, and it is not a future. And then it's clear, you see there is the different antibodies here, the growth rate, and why all the companies actually hop on actually antibody developing, manufacturing, and so on. So now let's go back to a question before we come to the downstream processing. Yeah? Because we have to manufacture this material. So what is a typical dose? A typical dose in the hepatitis B vaccine is about 12 microgram for an adult. So this is not a lot. Yeah? This is less than a grain of salt. Yeah? Somatropin. Yeah? You have about 26 microgram to 40 microgram per kilogram body weight and day. Still not a lot. Yeah? The same is actually for GCSF, is also about 10 microgram per kilogram body weight and day. But now we come to these antibodies, and here you see some of these best sellers. Yeah? Herceptin, Humira, we have about 40 milligram per kilogram and body weight every week. Yeah? So we are already in the gram scale, yeah, per dose. The same is for Herceptin. Yeah? So now you see what is the annual production. The annual production is actually for the full-length antibodies is about 8 tons per year, and the recombinant proteins produced by microbial fermentation is also about 8 or 8.5 tons. Altogether is 18.6 tons. So this is the annual production worldwide. So that, you see, fits into a freight wagon. Yeah? So that fits into a freight wagon. So now think about the German steel industry, 2015, yeah, produced 37 million tons with a revenue of 42 billion. Yeah? And these are 2 million freight wagons. Yeah? So when you see now 1 gram biopharmaceutical sells for about $10,000, 1 gram gold for about 40, and 1 gram steel less than a cent. Yeah? So now you see that this biopharmaceutical industry has a completely different focus when it comes to development, manufacturing, purification, and so on, compared to other industries. And therefore it's also rather difficult actually to adapt methodologies, yeah, technologies from other industries. Yeah? And actually we are still working at a very, very small scale. So now another question, and why is this high price justified? Here we have actually an antibody, just as an example. Yeah? And those of you, especially my students, they should know, yeah, that such an antibody is not a single molecular entity. it can be modified on each point here, yeah? And this is what is called post-translatorial modification. I don't go into the detail. But here you see the possibilities of this post-translatorial modification, and then you actually calculate with this permutation, the number of possibilities, yeah? And because this antibody is composed of two chains, yeah, this modification could be not symmetrical, could be also asymmetrical, yeah? And then we have this 16,920 to the power of 2, and this is 280 million different variants. So one single antibody, in theory, yeah, what we call monoclonal antibody, can contain 280 million different molecular entities. Yeah? So actually, and this is actually very unique for this industry. Also the regular pharmaceutical industry usually work with a very defined compound. Yeah? So, and therefore, maybe you heard about biosimilar. Yeah? So a lot of companies started to make biosimilar. So this is the biological equivalent of a generics product. And so what you have seen, it is extremely difficult now to make an identical product. Therefore, also the health care authorities and legislation said we want to have a similar product because it will be never, at least in our actually age, never be possible to make an identical product. And therefore, you have a reference product, and then you could make an identical, a similar, or a non-similar product. Here, this is actually how the antibody would actually behave in our bloodstream when we get it injected. Yeah? Then it will rise, and then actually after a few days, level off again. Yeah? So, and then here we have similar behavior, and we have never identical behavior. So now I gave you actually an introduction in biopharmaceutical industry, how I actually see it, and what is my background actually to develop projects. And Professor Gerzabek already mentioned that I am actually also interested in the fundamentals. But before we go to the fundamentals, I will show you a further challenge. When we start our purification, we have actually impurities, yeah, in the range of higher than 500,000 ppm. And at the end, we want to have less than 10. Yeah? So with the host cell DNA, it's actually we start also with a very high value. Yeah? At the end, we have less than 10 parts per billion, yeah? Or 10 picogram per dose. And so you thought about actually an antibody, one dose is 1 gram, 10 picogram per dose is not a lot, yeah? So, because this is the range of actually 1 parts per billion. And this is the reason why actually downstream processing is so important and also has such a focus in pharmaceutical industry. The discipline, Reingard, has been actually coined the term has been coined by Malcolm Lilly, professor at University of Birmingham, and then UCL, University College London. He dealt, actually split this up in upstream processing and downstream processing. And for the antibodies and for a lot of pharmaceuticals, actually we have this type of purification. You have the bioreactor, you centrifuge, capture, purification, polishing, and then for the mammalian cells, we have also this virus filtration. Yeah? So, this year, actually, not this year, it has been actually shown that the company Biogen, yeah, has developed an antibody which is quite successful in clinicals, actually to not prevent Alzheimer, but to dramatically slow down Alzheimer's disease. Yeah? And then the first time we would have to manage 50 to 100 tons per year. And actually we have to see This process, how we are today, is not suited. It's only suited for the singleton scale. So now let's go to the fundamentals. Yeah? So when you go to the fundamentals, it's very important because to be in Vienna, because you go to the National Cemetery, and then you have the tombstone of Boltzmann. And there is engraved what is the entropy. And entropy has a lot to do with separation science. So for those of you who do not know entropy, I now use this Smarties. Yeah? So you see these Smarties are mixed up with different colors when I actually pour them out. I should have tested this before. Yeah? So these are, let's say, these are our antibodies with the 285 million different variants. Yeah? But these 285 million variants are a lot of actually contaminated with other actually impurities. These are host cell proteins, for instance. This could be the DNA, lipids, and so on. Yeah? So, what has this to do with entropy? Actually, it is not possible that this antibody separates spontaneously. Yeah? So that actually the red ones come out by themselves spontaneously. This is not possible. There is a formulation, second law of thermodynamics. This would hurt the second law of thermodynamics. I don't want to go into this detail. We have a few experts here in thermodynamics. Yeah? Unfortunately, Professor Fischer could not come. Yeah? He actually sent me a quite nice letter. So when we do with this purification, there was a guy many years ago, and this was Maxwell, and he actually made the Maxwell's daemon. So he said whenever actually a molecule, because in reality these molecules move, yeah? Nothing is static, yeah? They all would vibrate here. Yeah? So when these molecules move, yeah? When the red one is going to the right, the white one to the left, he only opens, yeah? So that the left one, the red one can go to the right, and the left one to the left. So Rupert Chelesnik had helped me actually to simulate this daemon. Yeah? So this is the ideal separation machine. Yeah? But this is ideal, and we know also with a lot of discussion with Professor Fischer, you see the red ones are not able to go to the left. They only can stay to the right. Only the white ones can go. Yeah? So this would be the ideal machine, but there's a lot of papers that the ideal machine does not work, because also information contributes to entropy and so on. So we want further discuss about this. So now you see, and this is less actually spectacular, these are the real separation machine. The real separation machine is, you see, here we have a lot of smaller columns. Yeah? You see, this is the scale, 25 centimeters, maybe half a centimeter to a meter, and here up to 1.5. This is the schematic separation machine. This is the chromatography column here, which is filled with beads, and then here you see really a microscopic image of these beads, which are actually packed into the column, and then the material is actually passed through the column, and the separation machine actually separates the good ones according to the affinity from the bad ones. Yeah? The problem is also, and I don't go into this in detail, sometimes also the separation machine eats up the product, yeah? And therefore, yeah, we have a very low purity, yeah? And there's some separation machines, they eat up a lot, yeah? So, yeah. So you have only 5 to 10% yield, yeah? But also separation machine eats sometimes the unwanted material, and this we call fouling, yeah? So now let's go to, sorry, I'm really fouled now. Yeah? A challenging outlook. You see, when you have such a column, you have a pressure drop. And the pressure drop is actually determined by what is called the column permeability, how permeable this column is. And here is plotted the specific permeability versus the void fraction. And you see, we are here with chromatography, we are here with material, what is called monoliths or convective media. So you can assume you could also pack the media like a sponge into a column. But what you see here, this is the present and here is the future. So when you think about have we reached the physical limit, in this case we have not reached the physical limit, there is actually room to go. Yeah? And also in ASIP, we have one project really dedicated to actually push the limits. Yeah? So now I give you two cases for preparative chromatography. And in preparative chromatography, dynamic binding capacity is the most important thing. I will show you what is dynamic binding capacity. When you load this material on a column and it passes through with a diffuse front, not a sharp front. So at the end, not to lose material, because you have saturated the column and some of the material will drop off the separation machine, yeah? You have to stop. Yeah? So again, fouled. So you have to stop. The higher the velocity, the higher is actually the fraction of the unused bed. Yeah? And this is actually related to dynamic binding capacity. And you see here, we have the effect of flow rate of the velocity on dynamic binding capacity. And we have two scenarios. One is with high capacity, a slow process. The other is a low capacity with a fast process. We don't actually know what is the optimal one, yeah, because this depends actually also on a lot of other factors. But we understand this. And then it is clear when we increase actually the capacity of this, then we will be much better off. Therefore, you see the companies over the last 30, 40 years made a race about dynamic binding capacity. But it is not only the dynamic binding capacity, what you see, it is also the residence time. Because the winner is definitely the most old-fashioned material, but the residence time is less than an hour. At that time, actually, and I did also chromatography, which takes several hours. And now it takes several days or even minutes. And then you see, this is the physical limit. We can definitely assume that a separation machine, our chromatography material, can be modeled or simplified as a area. Yeah? So, and then it definitely depends on the size of the molecule. If the molecule is very big, yeah, the monolayer capacity is high. If the smaller the molecule is small, the monolayer capacity is low. But there is actually an effect between actually the porosity or of the speeds, yeah, and actually the area. Here I borrowed from one of my guests, Egbert Müller. Yeah, you allow me. Yeah, so a slide he published. So it's publicly available. Yeah, so they published 2006 in Chemical Engineering and Technology. Yeah, actually was a special issue which I have edited. Yeah, so. You see, and this is quite interesting. I like this, yeah, because if we have only actually a two-dimensional arrangement, yeah, we are pretty fast limited physically. Now there is also the possibility that you add actually a layer of polymers, and then you have a 3D arrangement, and all of a sudden you can increase actually the capacity. Yeah. But here, actually, we could reach the physical limits. I come back, yeah, because the concentration of protein in a crystal is about 300 milligram, 350 milligram per milliliter. So the separation machine, the material takes up some volume, yeah. So here with this concept, we are closer, very close to the physical limits. Then think about you absorb 300 milligram of protein, and afterwards you desorb it, you reach actually solubility limit. Yeah? Sometimes it's even not possible because then the protein precipitates. The other thing is actually for the larger molecules, we have also monoliths. So monoliths actually, what I mentioned before, are this separation machine where actually we do not pack individual particles, we pack actually a homogeneous continuous phase into the chromatography column. And here this is drawn to scale, is actually baculovirus, which is actually purified with monoliths. Yeah? Here you see such a structure, electron microscopy, you see BOKU still, yeah, there. Yeah? So it's a pretty old a picture, and you see, these are the channels where the molecules or the virus can be absorbed. And here you see again what is we actually have reached the limits because what is plotted here, this is the volume which is applied during adsorption, and this is actually the adsorbance, and this is actually the pressure. And the material is filled up until we reach the maximum pressure for this actually device, yeah? And then we are done. So when we do this calculation, then you see the surface coverage, yeah? Then we have already 40%, so we have 40% of the separation area covered. And this is a rough estimate, yeah? It cannot be much more, yeah. So because with this rough guess, it could be also 60 or 70%, yeah. So therefore, nothing is left. Therefore, I mentioned we have to expand this limit to the void fraction. So how can you do this? Yeah? So we did actually a 3D structure of this monolith. You see here, this is the 3D structure. And what you can do is actually, you can actually then simulate the adsorption or how such molecules pass through, yeah, this monolith. Yeah? And then I think it is not the computer animation, but now you can think about in silico, we can change the structures and therefore maybe improve them. Yeah, so that's the way where we can go further. Yeah, so I did a work with Christian Jungreutmeier. Yeah, he worked at ACIP. Unfortunately, we had let him to go because we could not offer him a permanent job, and is now teaching at FH. So you see here what we can do. Then we made actually three-dimensional potential structures, yeah? And what you already see here, so this is the reality, and these are potential structures you can make in silico. And you see here, actually, the pressure drop, yeah? The pressure drop is 1,300 Pascal. So actually, this is a slide I would criticize for my students, yeah, because the font is too small, yeah. Sorry for that. Yeah. So this is 1,390 Pascal is the pressure drop. Here you see with this arrangement here, with this one, we have only 1,130. Yeah. With this one, we have 300, and with this one, we have 5,000. So this is 5,000 here. So we have some room to go from actual 1,300 to 300. That means a factor of 4, actually, we could improve it, yeah, by this. And this actually computational fluid dynamics tells us, yeah, if we have reached the physical limits or not. So with current technology, we have actually reached limits with area versus void fraction. Yeah, so that's clear. Some, I think also some mechanical stability of bed, the 3D arrangement of molecules, yeah? But we have to stick with this concept because the packed bed has the highest efficiency. Whatever else we do with membranes and so on, we would also go to a lower. So the future is actually new materials, design in silico, the reduction of unused bed, selectivity, speed up of process development. And therefore, we can go continuous, because with continuous actually we can help out a little bit to improve the unused bed. And it's quite interesting from Konstantin Konstantinov, yeah, from Gensheim, yeah, in Framingham, Massachusetts, has published a paper, actually he said that this continuous manufacturing can reduce 50% of the costs. So we did also a lot of work in continuous manufacturing, but we are from academia and nobody believes us. Yeah? So if somebody is from industry and make this statement, then it is valid. So the question is now how continuous is continuous? Because continuous can be a batch-wise operation, yeah, which is actually done in a repetitive manner. I took this picture in Kyoto at a small bakery where you see Japan is highly automated, yeah, where they did very nice actually automated cookie baking. Yeah? So the adjective continuous describes something that occurs over space or time without interruption, uninterrupted either in time, sequence, substance, or intent, and continuous things don't stop, not even for a coffee break. So we have done quite a lot with tubular reactors, you see here, and this is pretty simple. Such a tubular reactor, which inbuilt things, and then you can do a lot of these reactions in these reactors. The inbuilt thing is, for those of you, that the residence time in the reactor is much narrower compared without. Yeah? I don't want to go into detail, just to show a few of these lab scale reactors where we did continuous actually ethanol precipitation of antibodies. So this is how the reactor looks like. Yeah? And this work is one of my actually most highly downloaded work, because we got 12,000 downloads. Yeah, so that's yeah. So here is, for instance, you do the ethanol, the IgG solution at low temperature. So you cool this, then let it react, and then you harvest actually the purified antibody. So this is how the laboratory system looks like. What we have built up here. And then we have also done other continuous reactors. I brought one, yeah. This is actually Peter Satzer's toy, yeah. So he liked to play. So this is with this, and you see, I did not, in interest of time, go into this detail, yeah. Due to this high price, yeah, of biopharmaceuticals, yeah. Often is the biomanufacturing is done with disposable units. That means every time or every batch you have done, the factory is disposed. Yeah, it goes to waste. Yeah, so in steel industry you cannot do this, that you have the actually steel cooker thrown away after every batch. Yeah, but here it is possible. Yeah, I did not mention these things. So the summary is, for conventional chromatography we have not a lot of room. For continuous we can do the process identification. We know that the unit operations and elements are available, but we need more for monitoring and control. And we need robust processes. Yeah? Robust processes means that these batch processes are inherently transient. and we need self-regulating systems with a natural resonance. And if you go through hotel lounges and so on, and you all see actually a system which is self-regulating with a natural resonance, you have to make a video. Yeah, so that's because this system here is self-regulating. And we can also, in downstream processing, develop systems which are self-regulating, and then we have robust processes. Now let's go back the last few slides to the Maxwell demon. What we tried to challenge the demon, which is called nanomembranes. Yeah? So the nanomembranes is ultra thin membranes, very thin. Yeah. With 20 nanometer, yeah? So it has almost the magnitude of our actually compound, yeah? And then if this has the magnitude of the compound, we have a Brownian motion and we cannot distinguish is this here or here anymore, yeah? So it's called also a bullet-like transport. And the diffusion here is actually extremely fast. So closer to the Maxwell demon, but also needs a lot of chemistry. So what you do is kind of, you make with these ingredients here a thin film. And while the thin film ripens, actually pores are formed. Yeah? So here you see, actually, you then see these spores which are formed, and then you see also the thin film here with atomic force microscopy. Also, this work has done as a strategic project in ACIP. And then it is quite interesting because also they are very thin, they are mechanically extremely stable. They are also called a self-standing or self-supporting membrane, and you can immediately see when this membrane has a mechanical defect. Yeah, and then a nice drawing, yeah, hand drawing from Agnes Rodler. Yeah, so here you see what is our vision, and we are pretty close to come to this vision. In the nanomembrane, you put in actually a biological molecule, which is a transporter. Yeah, there could be a transporter for proteins, for small molecules, and so on. And then we are actually able to transport actually small molecules, yeah, or other compounds against the concentration gradient. Yeah, okay. And this is, we need some energy, yeah, and we need also some entropy because the information, yeah, but it might be possible. So our attempt is that we have either the glucose transporter, and we are pretty close to realize this so then a long-term goal, yeah, that came reality that we are closer to the Maxwell demon. Yeah. Also, I'm like confident we will never reach the Maxwell demon. So now the final slides, where to go, is of course the closer is process intensification. Yeah. So those in companies who would do process development would go process. Of course, acceleration, some overcome solubility, reduction of material consumption, higher specific material. But a lot of these things we could do in future where we say go in silico. But there will be also other possibilities, yeah, like biorecognition, self-assembly. So you could actually imagine that a molecule, yeah, assembles with the surface, and at a certain time it disassembles. Yeah? And this is also close to the Maxwell demon or the active transport. So this is actually the end of my presentation. Now it comes to say thank you. Say thank you is very difficult in a big audience, so not to forget anybody. I already said thank you to our rector. I also want to say thank you to my former professor in biochemistry. Yeah? Professor Merz. Yeah? I have to say that he really was able to encourage young students, yeah, with biochemistry, made us interesting in biology and biochemistry. Really, thank you for that. And we had also a kind of triumvirate, yeah, that was Professor Sleiter and Hermann Kattinger, those three, yeah. And actually they were at the very beginning of my career, very influential, yeah, and I have to thank them, yeah. Professor Sleiter with his pictures in ultra structure, and also going to the lecture without a tie. Yeah, so they impressed us. Yeah, and Hermann Kattinger about the vision, what big we will do. Yeah, so. Then, actually, I have to thank all the companies we have worked for quite a while, maybe also quite successful, and I think also for their support, but I think we also have provided something for the companies, and we got a very nice compliment from the company Boehringer that somebody told to Boehringer people, you are actually lucky because you have infrastructure and people here in Vienna we don't have. So, and then I had funding, a lot of funding from FFG, from actually our Austrian Science Foundation, and I had several projects several projects with the European Union. So, after we do this deep scientific discussion, yeah, here, we actually will also have a wine, yeah. Alfred Zöchling, actually, he did the thesis together with me, and this is not my own subject. Also, I'm interested in wine, but it's seriously, yeah. So this is published American Journal of Enology and Viticulture, or Food and Function, yeah. So this is highly rated journals, yeah, about red wine. He was so generous and to make a wine on behalf of my Antrittsvorlesung, and I have another postdoc, yeah, Nico Ling, yeah. He spent also quite a while in Singapore. He is now Wappler Brewing, yeah, and he has brewed a beer, and this beer won recently a prize at which competition or fair? Okay, good, yeah. Good. Then definitely I want to thank my senior scientists and also colleagues, Astrid Thürauer and Rupert Czelisnik. Then Rainer Hahn, actually, he walked quite a while together. We had the same actually way, yeah. Verena Beck, which is now actually supporting me a lot in ACIP. Then you also Petra Polak, yeah. She is really behind the scene to organize these things, yeah. And then also I want to thank Karl Bayer. He's really encouraged me a lot and was my mentor, yeah, I have to say, yeah. The former students and the present students, because without them I could not have done this, especially what Professor Gerzerbeck mentioned, 320 publications, yeah. The department chair, Reingard, and also the former department chairs, yeah, actually for this good atmosphere. And also my family, which is here, and especially my wife, Monica, yeah, because Professor Gerzerbeck already mentioned that I'm often not at home, traveling somewhere else. Yeah. So 1, 2, 3 days is fine, but longer is not so fine. Yeah. But recently, you have maybe heard about in ORF was a documentation. Franz Wanritzky, he became 80, yeah, and then actually he was, his wife was asked about what has changed after he now retired, and then she said actually, then the things became difficult. So I have